All right, everybody, I think we're going to get started again. We're running about 5 minutes behind the schedule here. Our next speaker is Matthew Herr, and he's going to talk to us about graph-based modeling of the morphology of the synaptic spine head. Looking forward to it.
Yes, thank you. Hi, I'm Matthew, and I'll be talking today on work done at UC Irvine with collaborators at UC San Diego and the Salk Institute. The title of this talk is Graph-Based Modeling of the Morphology of the Synaptic Spine Head. This is the overview. For the background, we'll start with some general understanding of the simulation theory, including dynamical graph grammars. DGGs add a hybrid stochastic reaction and continuous modeling component into a graph-like representation. Next, I'll make some comparisons to functional programming between that and the mathematics of DGGs. Then we'll go over the implementation and biological theory behind simulating actin filaments within a membrane enclosed compartment. There will be an overview of the three main modules of the implemented rules. How the actin cytoskeleton plays an important role in shaping the morphology of the synaptic spine head will be covered, as well as the general theory of the actin cytoskeleton. Then equations for devised biomechanical rules will be provided. The next section will be on the example rules and a code snippet to show ease of implementation and expressiveness. Lastly, for this section, there will be an explanation of the algorithm implemented in the Mathematica package called Plenum for the hybrid OD stochastic simulation algorithm. The results are mainly twofold. There's a network and modeling component without a membrane, and there's the membrane size that doubles in acting in accordance with the actin cytoskeleton. Then I'll provide some information on future work. Here's the background. So, just like how languages can be formalized into grammars of strings, graphs can be formalized using graph grammars. They specify what patterns to consider within graphs, as well as how to generate new graphs from pre-existing ones. There are rules for each comprised of a left-hand side and a right-hand side, with the left-hand side being used to pattern match and the right-hand side being used to transform the matched subgraph. The dynamical component adds a continuous OD system to the stochastic simulation algorithm. Graph grammars can be used to model graph-like structures in biology, opening or leading to an exciting realm of modeling and simulation. There are similarities between DGG modeling and functional programming, as both of them are modular and expressive. For time evolution rules that change the state of the system, they can compose with one another, and this is related to function composition. The time evolution operators themselves can be formed in terms of annihilation and creation operators through what can be considered as higher order functions. The time evolution rules, and then these time evolution rules are handled with a backend simulation algorithm, and the rules are coded declaratively and in accordance with the mathematical theory. Here's the biological implementation and simulation. So the three main modules of the rules are network remodeling, biomechanics, and spine head membrane. So network remodeling is how the structure of the graph dynamically changes. For example, elongation and retraction of the pointed and barbed ends. And these have asymmetrical rate constants. And then there's a severing in the middle of the filament with a molecule known as cofilin. There can be capping of the barbed ends to prevent it from changing, which is through either polymerization or depolymerization. Then there's the bundling molecule called CAM kinase 2 beta, which strengthens filaments by binding them together. And this calcium molecule, this CAM kinase 2 beta molecule responds to calcium influx into the compartment. So this can be related to the signals it's receiving from the presynaptic neuron into the postsynaptic compartment. Then there's the molecule that adds a lot of complexity to the network called ARP23 that causes it to branch at about 70 degrees. The ODEs for the continuous part are used for synthesis and degradation of the molecules. Actin ATP can be attached to each actin molecule, the ATP part, yeah. And it can dissociate to ADP while it's on the filament. And through an intermediate of ADP plus inorganic phosphate. Cofilin can bind to the filaments as part of the filaments as well. And it can recruit more cofilin to its adjacent places through binding amplification. The biomechanics rules that change the spatial parameters contained within actin objects have 3 submodules. These are the stochastic angle mechanics that minimize the angle within a sampling of 3 actin objects. And then there's the anisotropic buckling, which also considers the trinodal system like the rest of the biomechanics rules. And this relies on a Lederer-Jones potential. Then there's the Hessian Boltzmann sampling, which is related to thermal noise of the Hessian of the Lederer-Jones potentials, which is related to the second derivative. And for spine head membrane rules, there's the area rule related to the difference between inner and outer pressure, causing it to shrink. Then there's a line tension related to the phase boundary, and Hoffick energy related to the curvature of the membrane to keep it smooth. Then the actin object attachment rules can attach the ends of the actin objects onto the membrane when they intersect. And then these can dissociate to a working filament, which can provide propulsive force from the actin filament onto the membrane, causing it to grow. And then these actins can deattach from the membrane, leading to the curvature of the membrane taking over and no longer being a part of connected to the same ID as a spine head membrane vertex. The figure on the left shows a dendritic spine in which actin has provided structure to a bulbous projection off of a dendrite. And the dendrite is the neuronal projective network that receives signals for a neuron. And the system considered here, known as the synaptic spine head, is much smaller compared to an entire cell. And it's just a protrusion off of it in the dendrite. And by a mechanism interacting with the membrane, the actin cytoskeleton is known as the major player in determining the morphology. Below it is a pair of actin filaments. One of them has been severed, and you can see that the actin ATP associates at the barbed end mainly, and as time progresses, it converts to ADP and depolarizes from the other end. So there's the ARP23 branching to create the daughter filament, and the capping protein prevents the barbed from changing further. And to the right is the formatted DGG rule, where it shows the graph structures of the left-hand side and the right-hand side. In the with clause, there are two main components. One of them is the rule-finding propensity, and the other is the sampling distribution that is conditioned on the input left-hand side. So this is for the branching rule, and when it's incorporated with barbed and pointed end rules, the resulting simulation is shown below it. Here's a little more theory on the actin cytoskeleton. The actin ATP favors polymerization at the barbed end, while aged actin ATP favors depolymerization, and this process is known as actin treadmilling. And this causes the cytoskeletal network to move outward towards the barbed ends and retract from the pointed ends. And ARP23 creates a greater network field. And cofilant has the opposite effect of ARP23, and it can sever the filaments in between, causing the pointed ends, exposed pointed ends, to depolymerize. And it can bind all the way to the barbed end when it's capped, while possibly severing along the way. When it reaches an end, it increases the uncapping rate and lowers the barbed end polymerization rate, and also increases the pointed end depolymerization rate. And the severing occurs mainly at boundaries between covalent bound and unbound sections. So this mainly occurs towards the pointed end more frequently than the barbed end. This molecule that we're considering of importance here is CAM kinase 2 beta, which gives the compartment some form of memory. It binds and strengthens parallel filaments into bundles, leading to a stronger force onto membrane. And the number of these active molecules that have a structural role depends on the history of calcium influx into action potentials. Biomechanical rules are implemented such that 3 linked actin objects are sampled, and the middle object changes its spatial parameter due to the potential derived force. And this is either angular mechanics, buckling, or thermal noise. The mathematics of the movement toward the midpoint for the angular mechanics is mathematically equivalent to the sum of the squared potentials in vector form. For the buckling, the Lennard-Jones potential is shown with a repulsive term and a attractive term, and this causes anisotropic movement because it's optimizing the lengths simultaneously of 2 potentials within that 3-node system. And for thermal noise, this is the Hessian that provides a non-zero force when the gradient is near 0, because it's relying on the curvature of the Lennard-Jones potentials. Here are some example rules formatted for biomechanics and a code snippet. For the Hessian thermal noise, the sampling can be as part of the with clause, and it's there's what's known as a heat bath probability function that accepts as a Boltzmann probability the proposed update. And the reason for this implementation is this can accept larger updates more frequently, and it calls for a more efficient minimization of the spatial parameters. And for Lennard-Jones buckling, there's the clipping term, which is for the case where the proposed term becomes too large, maybe due to atomic orbitals overlapping. And for the code snippet, you can see how this three actin objects are represented, one after another, using the IDs in the third and fourth parameters. And the actual IDs related for the objects are in the first position. So the rest of them are parameters that are necessary for spatial manipulations and related to other rules, including the nucleotides that I mentioned earlier. Yeah. And then up above is the left-hand side, and below it is the right-hand side. Work by a previous team has developed a time-ordered product expansion for stochastic systems that can be used to derive simulation algorithms. In this case, it has been used to mathematically derive an extension to a Gillespie stochastic simulation algorithm, ending up with a hybrid stochastic reaction differential equation model. We can factor out the rule-firing probability distribution into the firing propensity and conditional probability distribution. And that's, those propensities are mainly used to choose the right reaction, to sample the reaction to be executed from that pool of reactions. And the effective waiting time is drawn from the exponential function, because it's assuming a Poisson process. And there's a ODE that's solved in the middle of the algorithm. And using this update of parameters together with the updated parameters from the John reaction, this is considered a single step. So here are the results of some of the simulations. This is without the membrane enclosed compartment, and what we get here is a bimodal distribution of the filament lengths. This is consistent with biological theory that there's a dynamic pool and a stable pool, and this simulation is coarse-grained with a number of 4 actin monomers per circle, or per actin object. Here's a simulation with a membrane enclosed compartment. And the plots are related to the top simulation. I'll show the bottom simulation in just a second. And this also leads to the bimodal distribution with a coarse-grained number of 8. And the average biological spine height size is about 3.03 microns cubed. And a small one is about 0.01 microns cubed. So this ends up being about half the size of the small synaptic spine head. And the bottom simulation I'm showing here because there's more chem kinase 2 beta bundling across the centerline axis. And you can also see a kind of forward movement towards the barbed ends, and the membrane kind of pushing on the pointed ends. And this is consistent with biological theory that actin cytoskeleton can provide cell movement to cells such as bacteria. And the color of the actin objects is the degree of angle bending energy, and the triangles are the capped ends, and the hexagons that might be visible might be visible in the bottom simulation are the chem kinase 2 beta bundling molecules. The circles are coarse-grained actin objects. Here's the future work. So we'd like to implement within a computationally accelerated package, and there's one in development called Cajete, which uses parallelized approximate SSA that divides the space into grids. And then there's long-term potentiation. This phenomenon is important for memory and learning. And we'd like to model a decrease in area to steady state after an initial increase in area by changing synthesis rates, which encompass those molecules that can diffuse in and out of the spine head. And then through this, we'd like to find the molecular drivers of learning and their effect sizes among different actin network regulators. This is the list of references on DGG formalism details and related works our research team have published. Thank you.
Thank you so much. So how is it determined where the branching on the actin filaments happens? Is that just a probabilistic determination of a possibility of branching at one point and then reducing the potential branching on that same filament later on, or how does that work?
So for the branching, it's there's a branching rate at which actin, for which the ARP23 molecule can add to match subgraphs along the filament, and there's a little there's this more in-depth mechanism where the ARP23 can be activated or deactivated. So there can be portions along the filament where a deactivated one attaches and actin objects don't attach further. Yeah.
Thank you. That was a great presentation.
Thank you.
I'm curious about you showed your TOPE algorithm.
Yes.
And I'm curious about is it sort of similar in spirit to like the approximate multi-step algorithm tau leaping, that Dan Gillespie proposed 20 years ago. Is it similar to that, or is it an exact algorithm?
Yes, it's an exact algorithm. Yes.
Okay.
Yes, I think it's slightly different actually, this one tries or wants the rules firing in order, and then yeah, that's the extent of my knowledge of that comparison right now. Yeah.
Thank you.
Yeah, no problem.